we're going to deal with friction. And so friction is, well, it's fairly intuitive. You've all dealt with friction. So, but let's talk about, let's just review a little bit. Like if I have a crate like this, and I put it on wheels, and I pull on it with a certain pulling force, F sub P, and this has a certain mass. Well, I mean, what do wheels do? Why did we invent the wheel? We invented the wheel so we can move things that are pretty heavy across surfaces easily. Now, if I was to draw a free body diagram of this situation, I would draw the object. I would draw the mass times gravity, which would give me the weight of the object. And I just usually write it now as m times g. Because I usually give you mass, and then you figure out the weight, you multiply mass times. And what is g? 9.8 newtons per kilogram. If you want to do meters per second squared, you can, but it's not accelerating down, right? So it's gravity pulls down with 9.8 newtons of force per kilogram of mass. So that's the way. Now, the reason the object isn't accelerating is that, like on the wheels, but we'll just make it one force. We've got a normal force like this, and we've got this pulling force. And so here's my free body diagram of this crate being pulled across the floor. But what if I broke the wheels off? And now I'm pulling like this. Well, I think that, you know, it's pretty logical to that there's going to be a new interaction between the floor and the crate. See, what is the normal force? The normal force is the interaction between the floor and the crate that is perpendicular to the two surfaces, to the surface of the wheels here and the floor. That's why we call it the normal force, because in mathematical language, the word normal means perpendicular. So we could call it the perpendicular force, which I wish we did actually. So if let's say I'm pulling this across with some velocity, we're dragging this across. It's like here's my coffee mug, and I'm pulling on it, and I'm dragging it across the table. Well, if I was to draw a free body diagram of this, okay, well, I'd have the pulling force. I'd have the same weight. I would have the floor is still supporting that weight, right, with the normal force. But now we've got a new interaction between the two surfaces right here. And that interaction we're going to call friction. Now it's spread out all along the bottom of the two surfaces where they're touching each other. The friction force is kind of spread out over that surface, but we're going to write it as one force on the free body diagram, and we're going to call that the friction force. And the normal force is the interaction between two surfaces that is perpendicular to the surfaces. But the force of friction is, let me zoom in. The interaction between two surfaces that is, well, what's kind of the opposite of perpendicular? It's parallel. Okay. So we've got an interaction now between the crate and the floor. One of those, we're going to split that interaction up into two parts. The perpendicular part, which we call the normal force, and the parallel part, which we're going to call the force of friction. Now, what causes friction? Well, if I was to look at a microscope at the bottom of this surface, it's not going to be perfectly smooth. It's going to be a little jagged like this. And so that's the bottom of the crate. And here's the bottom of the floor. We'll have the same kind of thing. It won't be perfectly smooth. And so there's that surface. And so when you try to pull this one this way and this one this way, they're going to bump into each other, and there's going to be little forces. And also, when you have, these are made out of atoms, right? And atoms sometimes form bonds between each other. And so there's a little bit of bonding that can go on between the atoms of these two surfaces that can make it sticky. Now, how sticky they are between themselves depends on the materials. If you have steel on ice, the force of friction is going to be very low. Like if you have an ice skate moving across ice, it's very, very low friction force. Whereas if you have rubber on asphalt, you have very high friction force. You know, those two materials. So it depends on the materials, and we're going to talk about that later on. But this is the so we're going to define friction to be the interaction between two surfaces that is parallel to the two surfaces. Okay. Well, now you can we can do a little demonstration of that right now. I want you to put your hands together like this. Little school prayer here, okay? Now, I want you to barely touch your hands. Like you can barely touch. You're not pressing your hands together at all. You're just barely touching them, and then you try to rub them together, right? There's not much friction there, is there? No. I don't feel much. Now, press your hands together harder. Now, what am I doing? I'm increasing the, no. If I'm not even rubbing them together right now. I'm just pressing them together. What am I pressing together?
Pressure.
What kind of force? What kind of force is perpendicular to the two surfaces? I'm increasing the normal force between my hands. Now, if I increase the normal force, now let's see how much friction I get. Oh, I get a lot more friction, don't I? The more normal force, the more friction. Press harder. Harder. More normal force, what do I get? More friction. Press harder. Go.
Fire.
Go.
Fire.
Okay. That was Alex. He got a little excited. Yeah, he got a little excited. All right. Okay, yes. I mean, you could literally start fires that way. You know, one time I was running and I tripped and I fell and on my elbows, and I rubbed my elbows against the carpeting after I fell, and I got burns from it. I mean, you can get burns from that. So anyway, so look, I think that it's reasonable to assume that if I have more normal force, I'm going to have more friction. Okay? So that's the relationship that we want to explore. The harder we're pressing two surfaces together, the more friction we get. I think that makes sense. Now, let me show you this. I have a little demo. Let's zoom all the way out. And I've got a spring scale here. And I'm going to start it on 0. Always 0 the spring scale. And I got this little paper envelope that really has almost negligible mass. Does it have mass? Yes. So does it have a normal force between the envelope and the table?
Yes.
Yes. Can I measure it? It doesn't even move the scale. Okay, when I pull this thing, it doesn't even, So we're going to say that we have a negligible envelope here. But that's not like negligible. Okay. And so we're going to pull on this. Now I want you to it barely fits. Let me do it. Put it closer. So what I'm going to do is I'm going to pull on this. Let me refocus that. A little out of focus. So I'm going to pull on this. Okay, ready? Ooh, 1 Newton. 1 Newton. Do you see that it's on 1 Newton? Maybe not, but it's on 1 Newton for those of you in the back. It's not accelerating, is it? So if I'm pulling on this with 1 Newton, this should be accelerating at 1 meter per second squared because it's 1 kilogram of mass. But it's not. Why? Friction is pulling the other way. Okay, now let's go to 2 newtons. Oh, do you see it move a little bit? Okay, it's moving a little bit. Okay, but now here's one thing I want you to see. Okay, I'm going to do this. This is going to be exciting as it gets. I'm going to pull with 2 newtons. Do you see that I'm pulling with constant velocity? Constant velocity means there's no acceleration, huh? Okay. Now what I'm going to do is this. Double prizes. All right, I'm going to re-zero. And now I'm going to pull on this. 1 Newton, nothing. 2 newtons, no acceleration. 3 newtons. Oh my gosh. Oh, I got up to about 4 newtons and it started moving. Okay. Now, so we've got, and then if I pull it like this and I pull it with constant velocity, I get a force of friction that I need. So we're going to talk about 2 kinds of friction here. One of them, when it's not moving, let's put it right here. It's not moving. We have a word for not moving, or not accelerating, actually. It's called static. Have you heard that word before, static? Static is a fancy mathematical physicsy way of saying it's not moving, or it's not accelerating, really. It's in equilibrium. It's a static situation. Things aren't changing. Okay, so we're going to do this. Let's talk about, let's see. I'm going to do this a couple times. Let's zoom in. Give it something to focus on. It'll go faster. So let's talk about static friction. So here's my, I'll just do it with a crate. Here's the surface. Here's this. And we're going to say V equals 0 and A equals 0. And I'm going to pull on this with the pulling force. Now let's draw the free body diagram. And we've got mg like this, the weight of the object, and then this is the normal force. Do you see that the normal force in this situation is just equal to the weight? You can sum the forces in the y direction and say, oh, the forces are just, this normal force is just supporting that weight, because it's not going to accelerate up or down. But now let's say I barely pull on it. Little tiny pulling force. Well, what's my friction going to be? Little tiny baby friction. All right? Because if the acceleration is 0, what has to be true between the pulling force and the force of friction? They have to cancel each other out. Does that make sense? Now what if I pull on this with twice as much force? What's going to be true about my friction? Well, if it doesn't compensate for it, the object would start accelerating. But I'm saying it's not accelerating, it's staying at rest. So let's measure this. And then we'll measure this. Now, let's say that this is the maximum I can pull on it before it starts to slip. Well, then what we're actually measuring by measuring this maximum pulling force is we're measuring the maximum force of friction that I can get with static friction. Okay? So the static friction, and I'm going to call this a force of friction sub S. See how I've got two static friction. I'm going to call it F sub S. What does that S stand for? Static. What does this little f stand for? Friction. What does this big F stand for? Force. Force of friction that's static. You can say it whatever order you want. And these two will be equal to each other until you reach the maximum. Now let's talk about kinetic friction. Let's suppose you've got a surface and you're going to pull this thing across this surface, but now the acceleration is 0. Now you had to have some acceleration at the beginning, right, to get it going. But once you got it going, we're going to say that the velocity was constant. See, with static friction, the velocity is 0. But with kinetic friction, we're going to have a velocity. But we're going to do the experiment such that it's constant. And you'll see why here in a second. Because let's draw the free body diagram. Oh, and guess what we're going to call this? F sub K. Oh, by the word, wait, I haven't said this before. The word kinetic is a fancy physicsy way of saying motion. Something is in motion. We have kinetic friction. That's the friction of relative motion between two surfaces. We're going to have kinetic energy later on. So anyway, kinetic means there's motion. So I'm going to have this pulling force, and I'm going to have this force of kinetic friction, and I'm going to have our weight, and I'm going to have our normal force. But if the acceleration is 0, if I sum the forces in the x direction and say that's equal to ma in the x direction, then I'm going to say, okay, well, this pulling force We'll say this is positive x and this is positive y. Well, minus the force of kinetic friction is going to be equal to ma, but a we stipulated. Let's move this across the table at a constant speed, so that's going to be 0. So the pulling force is going to be equal to the force of kinetic friction. Now, if there is acceleration, then your pulling force has to pull with a force greater than your kinetic friction because you need a net force to cause acceleration. But we're going to say for the purposes of this lab, we're going to do this. Now, so I think what you can see is this, that if you measure the weight, you really know what the normal force is. So we can't directly measure normal force, but we can directly measure weight. And if we say, well, the forces are equal and opposite here, because it's in equilibrium, so the normal force has to be equal to the weight. And here, the object is not, well, in both cases, the object is not accelerating, so the pulling force and the force of friction have to cancel each other out. So if you measure the pulling force, then you know what the force of friction is. So here's what we're going to do. We're going to do 2 different labs. We're going to answer 2 different questions. If you're in group 1, 2, 3, and 4, this is the question you are going to answer. How does maximum static friction depend on the normal force? Okay? So how does blank depend on blank? Well, how does the maximum static friction depend on the normal force? If you are in groups 5, 6, 7, 8, or 9, you are going to answer this question. How does kinetic friction depend on the normal force? Okay? Now, you guys are going to have to write a procedure. So draw a sketch of your lab and then steps. Step 1, step 2, step 3, and so on. Don't forget to do that. But now you're going to have to collect data. So leave room to write your procedure after you've collected your data. Then you can write up how you collected that. But we want to know what the normal force is in newtons. And we want to measure that force of friction. Now you put a K if you're in groups 5, 6, 7, 8, or 9. You put a S if you're in groups 1, 2, 3, and 4. And I want, let's say at least 4 different measurements made. Now, how are you going to do this lab? Okay, I'm going to give you an envelope and a spring scale, just like this. The envelopes I'm giving you are bigger than this one. I just got this small one to do the, because it fit under the document camera, sort of. What you're going to do is put different masses on this paper. Start with lower mass, and then, increase the mass. And then what you do is you pull on it and pull on it and pull on it. You watch it very carefully. And then when it starts moving, what's the maximum force you see before it starts moving? Okay? And then do that for like 3 or 4 or 5 different masses. Well, but hey, what is the weight here? What is the normal force? If you put 1 kilogram on here, how much does 1 kilogram weigh in newtons? What is M times G? What is 1 kilogram times G? 9.8 newtons. So this has a weight of 9.8 newtons. So gravity's pulling this down with 9.8 newtons of force. So therefore there must be a normal force up to support that weight of 9.8 newtons. So you would put 9.8 newtons as your normal force. And then you're actually measuring the pulling force with the spring scale. But we're saying that since we're doing it with 0 acceleration, the pulling force has to be equal to that force of friction. Now for groups 5, 6, 7, 8, and 9, you're doing kinetic friction. What you do is you get it going and you make sure that it's moving with constant velocity. Don't accelerate it. Get it going and then move it slowly with constant speed across your table and measure the force. And it's a little tricky, but you just have to figure it out. Okay? Now, you can put lots of these 1 kilo, you're going to have to share the masses, and I'll get some more masses out, but you have to share the masses because you can put a lot of mass on here. And I'd like to see a big spread of mass, like anything from half a kilogram all the way up to like 5 or 6 kilograms put on this envelope. And then you figure out what the weight is, measure the force of friction, and then we'll see what we get. All right? Any questions on what you're supposed to do? Okay, that is all.